Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So tell us, Nick.
Well, thank you for the warm welcome. This talk is about a relatively new topic called network coding. And although the area is new, the problems that it seeks to address are very fundamental problems in how to transmit data through a network. I think it's a very interesting area with lots of interesting open problems. And there's a few people at Microsoft Research who think so as well. And so I hope all of you will find it interesting too. And this talk is about a new algorithm to construct network codes for certain types of multicast problems. And this is joint work with my advisor, David Karger at MIT, and with Kazuo Murata from Tokyo University. Here's the outline of the talk. I'll start off with a quick introduction to network coding to give some a basic background in the problem that we're trying to address. And then I'll give some background material about our approach, which is based on mathematical objects known as mixed matrices and a problem known as matrix completion. One of the key steps in our approach is an algorithm for computing the rank of a mixed matrix. So I'll go over that algorithm in some detail. Then I'll explain our algorithm for matrix completion, which leads to a solution for the original network coding problem. And finally, time permitting, I'll explain some of our more recent network coding work, which talks about a problem known as the k-pairs communication problem. One of the great things about network coding is that it only takes a few minutes to be convinced about what a neat area it is. So for those of you who've seen network coding before, just bear with me for a few minutes. And for those of you who haven't, let's start with a simple example. So I'll start off with this simple directed graph, which is probably familiar to many of you. This is often called the Wheatstone bridge due to its similarity to a circuit used in electrical engineering. So in this graph, I have two distinguished vertices, S and T. And suppose that they have a bit, B1 and B2, and they want to swap their bits. They want to send them to each other. So a common way to model this sort of problem is using a network flows type approach. We look for edge disjoint paths from S to T and another path from T to S. But unfortunately, no such paths exist in this graph. So the only path from S to T is this one. And the only path from T to S is this one, shown in blue. And the two paths intersect at this bottleneck edge. So we can't hope to find edge disjoint paths. But the really neat thing about this example is that it's solvable if we allow ourselves just a little bit more power in the model. Since we're sending data through a network, we could allow the nodes to manipulate the data a little bit. In particular, we'll allow them to do coding operations on the data. When I say coding operations, note I don't mean compression. And this whole talk will assume that all the data we send is incompressible. Okay. So in this case, we'll send the bits B1 and B2 to the top node, and then we'll XOR them together. Then we just send this XOR down the bottleneck edge and onwards towards S and T. Now S and T can decode their desired bit just by another XOR operation. So I think this example really illustrates the key lesson of network coding. When we talk about sending data in a network, we usually try to model it with the network flows or some sort of combinatorial packing approach. But when we learn about network flows in our sophomore classes, the examples we usually see are examples like sending fluid through a system of pipes or sending trucks of diapers to Walmarts across the country or something like that. But the lesson is that sending data is fundamentally different from sending diapers I can XOR data together, but I can't XOR diapers together. I think there might be some researchers working on that problem. If any of you make progress, let me know. I think that's a great result. Okay, so let's move on to more specific class of network coding problems. So a multicast problem is a problem where I have one source node, which has R messages, and we'll view these messages as being symbols in some alphabet sigma. In this talk, and in most of the literature on network coding, we'll assume that the graph we're working on is a directed acyclic graph, a DAG. And that's really because if the graph has cycles, then you need to exercise some care that you don't have feedback loops and things like that. So it just becomes a little bit more messy. So we'll stick with the DAG approach. Okay, and the graph also has k-sinks. And the important thing to observe here is that the sinks want all of the messages from the source. If they wanted some subset of the messages, then this wouldn't be a multicast problem. A network code is a function specified at each node that says how to compute the node's outputs from its inputs. And a network code is called a solution if it allows the sinks to decode all of the messages that they want. And there's a key result of Al-Swidi et al. And this result is that for multicast problems, a network coding solution exists if and only if there's connectivity R to each sink. And it's important to note that if we didn't allow network coding, this result would not be true. There are examples where you can have connectivity R, but no network flow solution. And another key result concerns the type of coding operations that we'll allow the nodes to do. Suppose we regard our alphabet sigma as a finite field. And now consider some node who receives inputs A and B. If we restrict the outputs of that node to be linear combinations of its inputs, then I'll say that the code is called a linear code. And the theorem of Lee et al. Is for multicast problems, it suffices to just consider linear codes. That is, if there is a solution using some more complicated codes, then we can always find a simpler solution that just uses linear codes. And this is good news because it means that writing down the coding functions doesn't take too much space. So we can find a solution that has polynomial size whose size is polynomial in the input size. So that's good news. Now let's consider how we're actually going to write down the solution. Well, our code just consists of a bunch of vectors at each node specifying how it should compute its outputs from its inputs. What linear combination of my inputs should I send out? So we can gather these vectors into a set of matrices. And then this way we can bring the tools of linear algebra to bear on our network coding problems. So first, for the source node, we'll have a matrix A, which indicates what linear combination of the original messages the source will send out on its edges. And then we have a huge matrix F, which specifies for each internal node in the network what outputs it's going to send as a function of its inputs. And note that there's just a single matrix F for the entire graph. There's not a matrix for each internal node. And finally, for each sink T, we have a matrix B sub T, which specifies what linear combinations of its inputs it will produce as the output.
Nick, how are the internal nodes? How's that encoded in the matrix? I don't see the map, and the other two are pretty obvious. I don't see how you.
It's basically the same way. It's just harder to show in the diagram. So this node here, for example, will receive some inputs. And let's say they're x and y that it receives as inputs. And then its output here might be some linear combination kappa x plus lambda y.
Yeah, but where does that node part of the? Does he just sit in some part of that matrix there?
Yeah, he'll have this column of the matrix.
He gets a column.
He gets a column. Yeah. And this node here, or actually it's a column per edge. Yeah. Right, so this edge gets this column, and this edge gets this column.
There are as many columns as input edges and as many rows as output edges, which is the same number of edges.
That's right.
Okay.
Yeah. So if there's m edges in the graph, then this matrix will have size m by n.
But so there's. Oh, okay. Oh, inputs are all together. I mean, we don't look. In other words, the internal nodes there between the edge between one internal node and another internal node, that's not expressed by this matrix.
Edge between internal nodes?
Between one internal node and another internal node?
It is.
That is as well.
Yeah.
So is the connectivity of the matrix expressed? Do we know that one guy's input edge is the same as somebody else's output edge?
You can kind of tell by where all the non-zero regions are, right?
Exactly.
The little rectangles of non-zero stuff.
I got it. Okay, I got it now. Thank you.
Okay, and for the sync, we have this matrix B sub t that I explained, and it's really the same thing. We're just filling in the linear combinations as columns. Okay. All right, and there's another observation that's worth making at this point, and that's that since we assume that the graph is a DAG, then we can order the edges so that this matrix F becomes upper triangular, and that'll turn out to be important in a moment. Okay. Now, let's try to understand when our network code actually solves the multicast problem. So each sync is receiving some linear combination of the source's messages. And if these linear combinations have full rank, then we can compute the inverse of these linear combinations. And then intuitively, we can see that the sync can use this to reconstruct the source's original messages. And there's a formalization of this as a theorem of Cotter and Medard. They show that the linear combinations received by a sync T are given by this matrix A times I minus F inverse times B sub T. And they call this the transfer matrix for sync T. And they show that a multicast problem has a solution if and only if the determinant of the transfer matrices for each sync are non-zero. But remember that the entries of these matrices are unknowns. They're variables. So we can't exactly compute the determinant using standard algorithms. In fact, it'll be a symbolic expression, and it might have exponential length. So we can't even write it down. So these transfer matrices they're a bit unwieldy to work with because they involve the inverse of that huge matrix I minus F. But we can instead define the expanded transfer matrix to be the matrix with this block form. This new matrix is nicer than the original transfer matrix because it doesn't involve any inverses. Each of its entries is just going to be either a distinct variable or a number. Okay, so we've defined this new type of matrix, an expanded transfer matrix. Is this useful? Well, yes. One can show that the determinant of the original transfer matrix is equal to the determinant of this expanded transfer matrix up to a difference in sign. And this is a pretty simple proof. It just uses the Chou complement. So now our problem's a bit easier because we just have to deal with these expanded transfer matrices. But the determinant is still of exponential length, so we still can't compute it efficiently. But here's what we do know. If we can find values for the variables such that each expanded transfer matrix has full rank, then the syncs can decode the messages that they want, and so we have a network coding solution. So before moving on, let's just recapitulate what we've seen so far about multicast network coding. We've got one source sending data to a bunch of syncs. Each node sends data on its output edges that's just a linear combination of its inputs. And our job is to find some good linear combinations. And these linear combinations are grouped into transfer matrices, which we simplified as expanded transfer matrices. These matrices contain variables in their entries, and our goal is to substitute values for these variables so that the resulting matrices have full rank. And if all the syncs transfer matrices have full rank, then they can decode the messages. So we've distilled our networking problem down to a more algebraic problem. This is called a matrix completion problem. Okay, so that's it for the network coding intro. Now let's talk about matrix completion a bit more formally. Does anyone have any questions about network coding before I move on? Okay. Well, let me know if you do. Yes?
Your goal is to, like, you said about two theorems about the existence of, like, network coding. You want to find them efficient. That's the goal.
That's right.
Nick, could you back up a couple slides? I just want to make sure I didn't miss something here. Back up one more. So the transfer matrix has this inverse in it, but when you go forward a slide, the thing that's the expanded transfer matrix avoids the inverse. So why?
That's right.
Is there a quick intuition for why you get away with that?
It's just a neat property of determinants.
Okay.
So
So it's a property of the relationship between the determinant and the determinant of the inverse.
it's if you have an expression that looks like this with basically the product of three matrices and the middle one's inverted, then there's a quick calculation you can do that shows that this determinant is in fact equal to the previous one.
Okay.
So it's just basically a little math trick.
And it's a trick you can do to avoid that matrix inversion.
Right. Right. And it's called the basic idea is this is called a Chou complement. This product of the three matrices.
Okay.
So you mentioned this work from 2000 which sort of introduced network coding, right?
Mm-hmm.
So did they not provide a constructive proof or constructive way of sort of showing how you can do this? Or I mean,
So the theorem.
I'm trying to understand. So how does the problem that you're trying to solve fit in with what was already done before?
Okay, that's a good question. So the question is how does this work fit in with what was previously done? So the theorem of Lee et al. Shows that a linear code exists, and it was somewhat of an algorithmic proof, but the algorithm requires exponential time. And this, a better algorithm was found by Jaggi and Chou and Jain and a group of others, and they basically improved on that algorithm of Lee and made it polynomial time.
Your goal is?
Our goal is to come up with another deterministic polynomial time algorithm for this. Okay. So previous algorithm, I'll list the algorithms a little later in the talk, but yes, previous algorithms were known that solved this problem. Okay. Okay, so let's move on to explain our approach. Okay. I'll define a mixed matrix to be a matrix that has entries that are either numbers or distinct variables. And so the expanded transfer matrices that we saw before are mixed matrices. And I'll define a completion to be an assignment of values to the variables that preserves or maximizes the rank of this mixed matrix. Yes?
Does the theorem assume that F is a large field? You'd think a very small field like 2 elements would have some funny case.
Okay, you're talking about this theorem at the bottom of the slide here. So, so this is a theorem of Lovaas from '79, and it says that if I have a sufficiently large field, a finite field f sub n, then a randomly chosen completion, a randomly chosen assignment of values to variables will be a completion with constant probability. And you're right, I'll give a lemma later in the talk. We don't actually need constant probability. We can get away with a smaller field. You're right. Okay, so so Lovaas's work basically gave a randomized algorithm for finding a completion. And it was an open question for 20 years as to whether or not a deterministic algorithm exists. And this problem was answered by Jim Gielen 20 years later. And he gave an algorithm to find a completion in f sub n that requires n to the 9th time. And this was later improved by him and one of his students to only n to the 4th time. Okay. All right. So does Gielen's algorithm immediately imply a solution to our network coding problem? Well, it doesn't, not exactly. One issue is that Gielen's algorithm finds a completion for a single matrix, whereas what we're interested in is a completion for an entire group of matrices. So we introduce now the notion of simultaneous matrix completions. Yes, John?
Matrices. What's the group of matrices? Or why do you say it's not a single matrix?
Okay, so for each sink, we have a separate expanded transfer matrix.
Okay.
And we want to find a completion that works for all of the sinks simultaneously. That way all of the sinks can decode the messages that they want. Okay, so we have this, so we'll assume we have a set of matrices, mixed matrices, n1 through nk. And each variable that can appear in at most once per matrix, but a variable can appear in several or indeed all of the matrices. Okay. And we define a simultaneous completion for n to be an assignment of values to the variables that simultaneously preserves the rank of all matrices. This leads me to our main theorem. If I let x be the set of all variables in these mixed matrices n, then our theorem is that a simultaneous completion can be found deterministically in time n cubed log n plus size of x times n squared, quantity times the size of n. And for a single matrix, the time is just order n cubed log n. We improve Gielin's result as well. Yeah, so basically, if we look at Lovaas's result was that if we choose a randomized completion, we can verify that by Gaussian elimination in order n cubed time. And the field that it operates over is f sub n. Gielin's algorithm is n to the fourth time, and it's deterministic, and that also operates over f sub n. So our algorithm works over a smaller field. For a single matrix, it can operate over f2. And it's faster than Gielin's algorithm, and it's a logarithmic factor slower than the Lovaas randomized algorithm.
And can you do a randomized algorithm for this as well? Thank you.
Yes, you can do a randomized algorithm for simultaneous completion as well. Yes.
It's like basically Lovaas algorithm?
Yes, you just need to work over a sufficiently large field. Yeah. Okay. Right, so if you consider, the Lovaas algorithm is basically, we look at the determinant, right? We view it as a multivariable polynomial, and then we use the Schwartz-Zippel lemma to argue about the existence of a non-root. And if you have several matrices, you can just multiply their determinants together, right? And use the same argument. Okay. All right, so before we can prove our main theorem, we need to explain in some more detail the theory of mixed matrices. This was chiefly developed by Murota. So he says that a mixed matrix A can be written as a sum of two matrices, Q plus T, where Q is a matrix containing only numbers, and T is a matrix that contains only variables or zeros. And it's pretty easy to show that the matrix A is equivalent to this block matrix A tilde in the sense that the rank of A is easily computed from the rank of A tilde. It just differs by an additive term of n. And now A tilde is a block matrix having these two identity matrices on the left, and on the right, we just have our matrices Q and T. Now our objective in making this transformation is so that the top half will consist of only numbers, and the bottom half will consist of variables and zeros. So for the bottom left identity matrix, instead of having I there, I'll actually introduce some new variables, z1 through zt. So I just replace it with this diagonal matrix. This is just to ensure that I've got variables everywhere on the bottom. Okay. So in A tilde, the numbers and the variables occupy distinct rows. Right? The numbers are all on the top, variables are all on the bottom. And such a matrix is called a layered mixed matrix. Layered mixed matrices are pretty nice to work with. The way I like to think of it is that they give us a divide and conquer approach for dealing with mixed matrices. We basically decompose the matrix into subproblems by putting all the numbers in the top and the variables on the bottom. So the top rows just consist of numbers, so we can just use regular linear algebra tools to work with them, computing the rank and finding independent sets of columns and so on. And how about the bottom rows? Well, it turns out that bipartite matchings are a convenient tool for dealing with these rows. And the basic idea is a theorem of Koenig and Frobenius from the 1930 or so. And the result is that if I have a matrix of variables or indeterminates like this, then I can associate with it a bipartite graph. Basically, I put one vertex for each row and one vertex for each column. And I put an edge between vertices I and j if the matrix entry I, j is non-zero. And the result says that the rank of this matrix equals the size of the maximum matching in this graph. And this theorem here is basically the key tool that we'll be using to avoid the exponential size determinants. We can get rid of that by basically looking at bipartite matchings instead. Okay, and the last ingredient in a divide and conquer approach is something to sort of glue the subproblems back together. And in this case, the main tool that we'll be using is matroid theory. For those of you unfamiliar with matroid theory, don't worry. I'll explain things at a pretty basic level, and it should be enough to follow the rest of the talk. John.
So is part of the idea in this theorem that you mentioned just that all I need to do is figure out which variables are important, and then assigning them later will be easy?
Yes, that's basically the idea. Yeah. So I'll go over that approach in a moment.
Okay.
Yeah. Okay. So we'll be looking at computing the rank of mixed matrices first, and this is an example of a problem where we can use matroid theory to glue the subproblems together. Okay. All right, so one result of Marotta is that the rank of A tilde can be computed by finding the largest sets JT and JB satisfying the two following properties. First, if we just look at the top rows of A tilde, the ones containing only numbers, we need to find a set of columns JT that are independent. And similarly, if we look at the bottom rows, we need to find a set of columns JB that are independent. And he says that the rank is just equal to the size of the union. And this result's pretty easy to prove as well. Basically just follows from the Laplace expansion of the determinant. Okay. JD, are you clear about JT and JB? Okay. All right. So now about the question of actually finding these sets of columns, JT and JB. Can we do this efficiently? Well, it turns out that we can. We can. This is actually a special case of something called a matroid union problem. So we can implement this by basically building the matrices, and then just implementing a standard textbook matroid union algorithm, and it'll find the sets for us. Okay, so now we have an algorithm to compute the rank of a layered mixed matrix. But remember, what we really want to do was find a completion. And it turns out that the two problems are pretty closely related. So let's take a closer look at the rank computation algorithm. So suppose we start with an LM matrix A tilde that looks like this. And the top half contains only numbers, and the bottom's got the variables. So we can split it into two matrices, MT and MB. And now our job is to find a set JT of columns on the top matrix and a set JB of columns in the bottom matrix. And the set JT has to be a set of linearly independent columns, and same with JB. It has to be linearly independent in the bottom. In order to find such sets, we need to be able to test whether a set of columns are linearly independent. So for the top matrix, that's pretty easy. We can just use Gaussian elimination. And for the bottom matrix, we can use the result of Frobenius and Koenig mentioned earlier. We can just use a bipartite matching algorithm. OK, so notice that we're using different methods to compute linear independence in the top and bottom matrices. Well, that's basically what a matroid is, at least for the purposes of this talk. From a programmer's point of view, it's kind of like a layer of abstraction, a subclass or an interface that you can throw on top of a matrix that allows you to change the subroutine for determining linear independence of columns. The subroutine's got to satisfy certain rules, certain axioms of a matroid, and different subroutines lead to different matroids. So in this case, the top one is just it's called a linear matroid, and the bottom one's called a transversal matroid. And you can show that these sorts of matroids these subroutines satisfy the requirements of a matroid. Okay, and so I talked about the matroid union problem, which is basically finding these two sets, JB and JT, whose union is as big as possible. And you could also consider the matroid intersection problem, which is finding ones whose intersection is as big as possible. And there are other problems you consider. One is called the independent matching problem. And it turns out, actually, that all these problems are equivalent. If we restrict to bipartite matching problems. So we can explain our rank computation algorithm in the context of any of these problems, in terms of matroid union, matroid intersection, or bipartite independent matching. So we'll give Marota's explanation in terms of independent matchings. Since we're using bipartite matchings anyways for the bottom matrix, it turns out that this independent matching formulation is the most convenient. OK, so here's the approach. We take our LM matrix, and we model it as a bipartite graph in pretty much the same way as the Frobenius and Koenig result. We associate vertices with each row in the bottom matrix and with each column in the bottom matrix. And we also associate columns we associate vertices with all the columns in the top matrix as well. And the edges on the bottom are defined just like the Frobenius-Koenig way. And for the top matrix, we just connect the corresponding rows, the corresponding columns in the two matrices. Okay, and so this defines a bipartite graph. I guess it looks kind of like a tripartite graph, but we'll view it as bipartite. We seek a maximum matching in this graph, such that the matching edges between CB and CT are linearly independent columns. So that's our goal. And here's an example of what such a matching might look like. So the matching edges in the bottom define a set JB, and the matching edges in the top define a set of columns JT. And so there's really a correspondence between the columns of the matrices and the edges that belong in our matching. And we'll sort of flip back and forth using this correspondence later on. OK, so let's get back to the rank computation. Basically, the plan is we'll just compute a maximum independent matching, JT and JB. And the algorithm will ensure they have maximum size. And the theorem told us that the rank of A tilde is just equal to the size of JT and JB. So that's it. That's the whole algorithm. And it was shown by Cunningham in '86 that the time to find he phrased it in terms of matroid intersection, but it's the same thing. The time to find this maximum independent matching is n cubed log n. And there's this was improved by Gabo and Zhu to n to the 2.62 using a very complicated argument, and as you probably guessed, using fast matrix multiplication. So it's not really practical. So for this talk, we'll just use the Cunningham version. OK, so far we've seen how to compute the rank of mixed matrix. Now let's talk about how to find a completion. So we want to find variables, or values for the variables that maximize the rank. So the plan of attack will be to use the rank computation algorithm to find this completion. So let's first look at completion of just a single matrix. To start off, we need a simple lemma. Basically, if we have a multivariate polynomial p whose exponents are at most d, then the lemma says that this polynomial has a non-root over any field fq where q is greater than d. And the proof of this lemma is pretty similar to the proof of the well-known Schwartz-Zippel lemma. The basic difference being that with Schwartz-Zippel, they're trying to show that a constant fraction of the points are non-roots. And in our case, we're happy with an exponentially small fraction, right? We just need one point that's a non-root. So that's why we can work over a smaller field. So this lemma immediately gives us a simple self-reducibility type algorithm for computing the rank. We have some mixed matrix A, where an X is the set of variables in A. And since the determinant is linear in every variable, then the lemma tells us that there's a non-root over F2. And so the simple completion algorithm basically says we just examine the variables in turn, we assign them the value 0, and we check if the rank has decreased. If it didn't, then great. And if it did, then we know that setting the variable to 1 will maximize the rank. Right? The lemma tells us it's either one or the other. So we just need to try one and see if the rank decreased. Another way of looking at this algorithm is basically using the method of conditional probabilities to de-randomize the Lovaas algorithm. So this algorithm is not terribly efficient if we just recompute the rank from scratch each time. Right? If you think about it, we're just changing the value of one variable. So the rank computation can't have been too different from how it was last time. So the basic idea is to reuse some of the rank computation work that we did before. And that'll help us do subsequent rank computations faster. In fact, it turns out that we just need to do one rank computation. So this idea leads to our better completion algorithm. Given a mixed matrix, the first step is that we compute the layered mixed matrix, A tilde, associated with it. And then we run the rank computation algorithm. But the rank computation algorithm gives us more than just this one integer as its output. It actually gives us a whole maximum independent matching. So we can use the structure of that matching to learn more about the matrix. And this will really guide us in our future, in the rest of the algorithm. So let xm be the set of variables corresponding to the matching edges in the lower half of the matrix after we run the rank algorithm. And so these are the important variables. As John pointed out, our goal is basically to identify the important variables. And that's what the set x sub m is. So there's a simple lemma that says that if we look at the variables that are not in x sub m, then we can just set them to 0. And this doesn't affect the rank at all. So those are very easy to deal with. And this is basically because the setting those to 0 doesn't affect our independent matching at all, right? Because it doesn't use those variables. So if our independent matching is still valid, and the size of the independent matching determines the rank, then we're fine. Our rank hasn't changed at all. So here's the pseudocode. Oh, here's the set x sub m, I should point out. Notice that we don't include the z variables in our set x sub m at all. And that's because we don't have to complete those. They were just artificially introduced to help us formulate the problem. We just need to complete the x variables. Okay, so here's the algorithm so far. And now how about the variables in x sub m? Well, they're a little bit more tricky. It's easy to come up with example matrices where setting them to 0 is a good idea, and other matrices where setting them to 0 is a bad idea. So we've got to treat them with more care. Let's see what happens if I assign one of them a value. So suppose I take x1 and I assign it some value v. Here v is not going to be a variable. It'll be some number, either 0 or 1, depending on the problem that I have. Okay, so when I assign it v, then basically the variable x1 disappears, and the edge associated with it also disappears. and the value of v appears up here in the top. Why does it appear up here in the top? Well, remember that our original matrix A was just q plus t. So if we take a variable and we assign it a value, it's basically zeroing out that entry of t and assigning the corresponding entry of q that value. Okay, but now we've lost the matching edge, right? Our matching, the size of our matching has decreased. And since the size of the matching determines the rank, we're kind of in trouble. We need to make our matching bigger again. How can we do that? Well, we'll notice that previously every vertex in CB had a matching edge associated with it, right? And now we've lost a matching edge, right? We lost this one right here. So we definitely need to make this column above it. That needs to be part of our matching now, right? Because this vertex needs to have a matching edge associated with it. So we need to add this column to JT. But notice that there are only 3 rows in the matrix, so we can't have more than 3 columns in our independent set JT. So we need to kick something out as well. We need to swap in this one column and kick out some other column. Can we always do this? Well, we prove something that we call the swapping lemma, which shows that you can. There exists a value v such that I can kick out this column C1 from the bottom matrix and add the corresponding column C2 to the set JT. And we show that there exists some other column C3 that I can add to the independent set in the bottom, and I can remove the corresponding column from the top. And so this would be the resulting matching after that. Okay. Now this lemma just guarantees to us that there exists some value of v. Can we actually find it efficiently? Well, yes, it turns out that you can. You can find the right value in just order n squared time. I won't go into detail, but the basic idea is to maintain Gauss-Jordan pivoted copies of Q. And using these pivoted versions, it actually turns out to be trivial to find out the value of v. So the only work required is doing the pivoting operations to maintain this pivoted version. And since doing a pivot is just an order n squared time operation, you just update each entry in the matrix, then this gives us the order n squared time to find v. That proves the theorem. So this is our whole algorithm. Basically, we find the important variables x sub m. The ones that are not important, we set to 0. And for the ones that are important, we use the swapping lemma and the Gauss-Jordan pivoting to find the good value v. And we just set those variables to their good value v. And the time required for this, the bottleneck is basically step 2, computing the independent matching. And as Cunningham's analysis shows, this can be done in n cubed log n time. So that gives us the time for the whole completion algorithm. Okay, how about simultaneous completions? That was our original goal. The basic idea is just to extend this better completion algorithm to work for a set of matrices. And the idea is that we'll just run it simultaneously on each matrix. And then when we have to choose a value v for a variable, you can show that for each matrix, there's just going to be one bad value of v. And if we run over a field where there's going to be one additional value that's not bad, so in this case we're running over the field fk plus 1, then there's going to be a good value. So we can just use that one good value, and it works for all the matrices. So that's the basic idea. So in summary, so this algorithm proves our main theorem. It shows that a simultaneous completion for n can be found over the field fk plus 1 in time k times n cubed log n plus x times n squared. And for the specific case of network coding, this gives us an algorithm for the multicast problem that runs in time order number of sinks times number of edges cubed. And so there's some related work that I briefly mentioned earlier, but I should point out. So the work of Jaggi et al. Is also a deterministic algorithm, and it's actually faster than ours. Their algorithm is more graph theoretic in nature, whereas ours is this different approach using more algebraic techniques. And there's also an algorithm due to Chou et al. This is a randomized algorithm. All these algorithms operate over fields of the same size. OK, so that's it for the multicast problem. So I'd just like to move on to some of our more recent work, which is what we call the k-pairs communication problem. So most work so far has been on multicast problems. And once we step outside that realm of multicast, things seem to get much harder. There are NP completeness results for some of the more general network coding problems. And for other problems, it's not even known if they're decidable. They could be anywhere polynomial time solvable to undecidable. So lots of open problems. One of the problems that we've been looking at is what I call this k-pairs communication problem. The setup is that we have some graph G, and we have a set of k source sink pairs. And each source wants to communicate some stream of data to its corresponding sink. And there's no correlation between any of the different streams of data. And the goal is to find the maximum communication rate between these pairs. So the traditional way to model this problem would be using some combinatorial framework like multi-commodity flows. As for finding a multi-commodity flow, you can find a fractional flow in polynomial time using linear programming, whereas the problem of finding an integer flow is NP complete. The question of so the problem that we're interested in is, does network coding allow us to find solutions with higher rate than multi-commodity flow solutions? And it would seem at first glance that the answer is no. I mean, for each data source, there's only one sink. So it seems there's no advantage in sending this data along extra paths and coding it with other streams of data, right? That's just going to, seems like it's just going to make things worse. But perhaps it's not so clear. So let's consider this graph. There are k sources on the top, k sinks on the bottom, and two bottleneck vertices on the left-hand side. Every source is connected to the vertex u, and the vertex v is connected to all the sinks. And also, every source si is connected to every sink tj, except for its corresponding sink t sub I. So basically, every source is connected to all the sinks that it doesn't want to talk to. And all the edges in this graph have capacity 1. So the maximum multi-commodity flow solution has rate 1 over k. And that's basically because the only path from a source to its corresponding sink goes through the bottleneck edge. So all the commodities have to go through this bottleneck edge. And so the maximum rate's 1 over k. Can we do better with network coding? Well, surprisingly, the answer is yes. With network coding, we can achieve rate 1. So this gives us, I'll explain the code. Basically, each source sends its data on all of its outgoing edges. So the node u receives all of the data. And all it does is XOR them together. It sends it downwards to node v. And node v sends this XOR onwards to all the sinks. Now, if we look at a sink, what do they get? Well, they get all the messages that they don't want, because that's what edges they have. And they also get from v the XOR of all these things, including the commodity they do want. So they can just XOR it again, and they extract out the commodity that they want. So this gives us a rate 1 solution. And so the difference in the gap between them is a gap of k. And since k is linear in the size of the graph, this gives us a theta n gap between the flow rate and the coding rate in this example. And I should point out this example was also concurrently discovered by Lee and Lee at the University of Toronto. There's another important detail about this example. With multi-commodity flows, the usual way to obtain an upper bound on the maximum rate is using what's called the sparsest cut. And in this example, the sparsest cut is the single bottleneck edge. And the sparsity of it is 1 over k. But with network coding, we achieve rate 1. So this shows that the sparsity is not an upper bound on the network coding rate in this graph. In further work with Bobby Kleinberg and April Rassal-Lehman at MIT, we've considered other approaches to obtaining upper bounds on the network coding rate. And I think April is coming out here in a few weeks to talk about this, so I won't go into further detail today. So we've shown that for directed graphs, there can be a huge gap between the flow rate and the network coding rate. What about undirected graphs? Well, it seems that the situation is pretty different. In fact, we don't know of any example where the network coding provides an advantage over fractional multi-commodity flow solutions. So this leads to our conjecture that the network coding rate, in fact, equals the fractional flow rate for undirected k-pairs communication problems, which is a significant difference from the directed case where we had order n gap between the two. We spent the last few months trying to prove this, and we've made some progress for certain specific types of graphs, but the general problem is still open. All right, that's the end of my talk. If you have any questions, please let me know. Yes?
Is there a way to generalize what you've been talking about to talk about privacy or security? That is, you were trying to show that if such and such, then these guys can talk to those guys. Can you flip it around and say if such and such, then these guys can't talk to those guys?
That's a good question. There are some people who've looked at the relationship between network coding and security. I think people at Columbia, John Feldman and Cliff Stein. I'm not familiar with that work too much, so I can't really comment on it. But if you want a pointer to look at, I recommend starting with their work. John?
You said when you got to the end of the matrix completion main part of the talk that there were solutions that were like the combinatorial solutions that were faster. So is the attractiveness of doing the matroid-based solution is that there's some hope that you can do better with it eventually as it's refined? I mean, it's a different direction toward the same problem. I mean, did Jaggi was Jaggi's faster solution around before your?
Yes, it was. So the question is, given that these other algorithms already existed for finding solutions, why bother coming up with another algorithm?
Yeah, is the attractiveness just that this is a completely different way of looking at the problem?
So in one sense, yeah, that's the benefit is we get a new way of looking at the problem. And since the field is so open, it's nice to have different approaches we can try out. In fact, our approach, because our approach is quite general, it's pretty easy to extend it to other variants of the multicast problem. So you could look at versions of the problem where, so one example is what's called a robust network code. You might have, so you have a graph where you're trying to multicast the data, and you might look at different sets of edges that could fail at different points in time. And using our approach, it's very easy to come up with network coding solutions that continue to work regardless of which edges fail.
And the graph theoretic approaches aren't as easily extensible to other domains, or to other variants of the problem.
That's right. Yeah, since our approach is so general, just taking a bunch of matrices and trying to complete them, right. You can just sort of vary what types of matrices you construct, and then complete those, and you end up with nice solutions to variants of the problem. Yeah, Bahab?
So you said for the multi-commodity case, for directed graphs, you can find the optimum network coding efficiently?
For multicast problems in the undirected case?
Multi-commodity. So
multi-commodity flow problems in the directed case?
Yeah.
I don't think any algorithms are known for finding network coding solutions to these multi-commodity flow problems. So the only algorithms for finding codes that I know of are for multicast problems.
I see, and it's NP complete to find it?
For multi-commodity flow problems?
Yeah.
That's not known. Yeah. So for most of these more general problems, nothing is known. Hardness is not known, algorithms are not known.
I'm having a little bit of trouble understanding the undirected statement because now you have cycles, and what do you do about this timing?
Yes, that's a good question. So even defining what a network code means in an undirected graph is a bit of a challenge. You have to ensure that, you have to worry about feedback along cycles and things like that. So I didn't want to go into too much detail because it can get somewhat complicated. There's a couple of different approaches. One approach is, the approach favored by the information theorists is to associate what are called delay variables with the edges of the graph, and then instead of sending, basically you view it as sending polynomials along the edges instead of just sending individual values. Another way to look at it is by taking the original graph and expanding it over time. So you create several copies of the graph. Basically, each copy corresponds to an instant in time. And then you direct the edges downwards between the copies. So this sort of effectively associates a delay of one time unit with each edge.
So you're making it into a DAG?
You make it into a DAG, that's right. And then you can reason about it as a DAG. Yeah. That's the basic idea. So for more information on this, I can recommend the thesis of April Rosal-Lehman, and she'll be talking about giving her thesis defenses on Wednesday as well. So.
Okay, let's wrap up the talk. Thank you.
It sounded like